Prof dekat Caltech, Prof Shankaro, Prof Theoretical Physics lah. So buku dia best. Saya selalu guna buku dia. So dalam ni ada tensile tak apa kan, tapi nanti kalau siapa-siapa yang minat on general relativity, mungkin waktu tu I ada, waktu Prof Ashraf, Dr. Ashraf kerja. So you know what's to do. Tan selalu join, so Tan we know something on this topic today lah. Okay, kenapa kita study tensor? Tensor ni dia lebih, dia kalau rank 1 tensor is vector, right? Vector is rank 1 tensor. Why vector is rank 1 tensor? Sebab daripada asal waktu the first day I talk about tensor, you all tengok I derive tensor daripada coordinate system kan. Itu semua 3D, 3-dimensional space, which is a vector kan. So the first rank 1 tensor is a vector. Macam kalau kita ambil vector biasa, you tahu vector biasa dAx I plus AY J plus AZ K. Okay. So and then kalau you cross product dot product dia A dot B, you become another tensor. For example, I mean you got the dia punya result which is let's say C katakan. So you boleh tulis AX BX plus AY BY macam tu, plus AZ BZ. You boleh tulis macam ni, ataupun you boleh tulis juga dia sebagai X ambil sebagai N B N N is to 1 until 3 dimensional, which is X Y Z. So this is result ni. So this is a product of a tensor lah kan. Product of a tensor. Apa ni, you boleh guna Einstein summation kalau in terms of Einstein summation convention. Nanti kita go to this Einstein convention ni, you akan dapat this is AN BN. So mana tak perlu letak summation simbol lagi, kita tahu. Dan N ni kita define from 1, 2 and 3. Maknanya space. Maknanya kalau 3-dimensional space, jadi N ni menunjukkan dimensionality dia. Maknanya 1, 2, 3. Kalau 3 dimension 1, 2, 3. So this is X. N ni this is for kalau X1 jadi X1, X2, X3. Maknanya X1 ni maknanya X, X2 maknanya Y, X3 maknanya Z. Kalau dalam spherical coordinate R, theta, phi. Kalau dalam cylindrical R, phi, Z kan. Dia boleh jadi macam tu. So dia, kalau kita tengok operation in tensor, kita tak perlu kita fikir R, theta, coordinate system, kita tak perlu fikir. Kita just operate whatever the mathematics behind dalam tensor tu. Right? We just do it. We tak perlu nak fikir kita buat dalam koordinat apa, kita buat dalam koordinat apa, tak perlu. That is the beauty of tensor. Tensor dia coordinate independent. Coordinate independence. So kalau kita bila kita dah buat collision sampai end result, baru kita nak masuk, nak tengok dia punya result, dia tengok nak measure whatever thing, nak tengok dia punya result in the physical form, baru kita masuk coordinate system. Maknanya during the operation we doesn't care about the coordinate system, we just operate dulu. So ini membuatkan tensor boleh handle kalau rank 1 tensor is vector. This vector is rank 1 tensor. Kalau kita tengok this is AX BY ni is rank 1 tensor covariant, contravariant. Rank 1 tensor whatever lah, ini N lah, kata N, ini N, okay. N, maknanya N boleh jadi 1, 2, 3. AN is rank 1 tensor rank 1 tensor contravariant. I think last week ada tunjuk cerita you apa contravariant covariant kan. Rank 1 tensor covariant. So kalau kita tengok rank 1 tensor covariant, it is a vector. Benda ni. So rank 1 tensor is vector. Kalau rank 0 tensor apa? Scalar. So rank 2 tensor, kita tak boleh kata apa dah. Kita kata tensor lah. The most orang engineering guna dekat engineering level, dia guna rank 2 tensor, which is stress tensor. Kalau you open dengar stress tensor, so itu dia orang pernah tengok stress. Tapi kalau kita physicist, kita guna untuk kaji ruang masa yang warp space time, warping space time, we need a tensor of rank 4. Rank 4, tensor of rank 5. Rank 4 lah. Tapi kalau higher dimensional lagi, if you go to a more higher dimensional space, maybe up to rank 5, rank 6 tensor. So tensor is coordinate independent system. So okay. And then, so kalau if in 3D we can handle tensor in 3-dimensional space, that is vector. Vector can handle tensor in 3-dimensional space. Rank 1 tensor can handle space of 3-dimensional space. What happened to what we call more generalized thing of space? We call it manifold. Pernah dengar manifold? You pernah dengar manifold? Manifold. What is manifold actually? Manifold in mathematics is a set of points. Everything is points, point. Tapi in a finite or in a closed system. Manifold. Tapi kalau space tu macam flat or infinite, that is not manifold. Okay, kalau is this universe is manifold, we don't really know. But maybe if it closed universe, kita tahu our universe is by itself is manifold. Closed universe. I mean, if you go far away, further billions of trillions, the 90 now observable universe is 90 billion light years away from us. The age of the observable universe is 90 billion light years. In a manifold closed universe, if you go even further than 90 billion light years, go further, you come back to the same point. I mean, just like Bumi, our surface of Earth is a manifold, so it is a closed surface. But we don't about the universe. We don't really know because the universe is so huge. I mean, bigger than 90 observable universe, like manifold bigger. Many times bigger lah. Okay. That's the manifold. And satu lagi konsep dalam tensor, when we belajar tensor, what is space and hypersurface? Space and hypersurface. Kalau in our 3D dimensional space is okay, we live in 3D space. Okay, so this is space. Okay, the 2D dimensional is surface. 2D dimensional is surface, and 3-dimensional space is space. But there is one dimensional less than 3D-dimensional space, which is 2D space. 2D space is a surface to 3D space. Okay, you tell me. 3D is a space. So if 2D is surface, okay. If we take the and then the 1D line is a line. But a line is 1D less than surface. Okay, 1 dimensional less than surface. Ni line is 1, and then this 2D space. So 1 dimensional less. We can call to the perspective of surface, line is its surface. To the perspective of one-dimensional space, 2D surface to us is a space to them. Okay. So 3D to perspective of 3D, 2D surface, 2D, 2-dimensional space is a surface. Okay. What if we have 4-dimensional space, like 4D space? In brain world, we have 4D space, up to 10-dimensional space. Okay. So this concept is this: is space, and to us, a 3-dimensional space is space. But to any, let's say, any being in this 4-dimensional space, this 3D is, they call it surface. Surface to them. It is a surface to them, because 3D is 1-dimensional less than 4D space. So what we call here, more general thing, we can say hypersurface. Hypersurface is n-1 less dimensional than surface. Kalau let's say we have space of n-dimensional space, so the hyperspace of this n-dimensional space is, hypersurface is n-1 dimensional hypersurface, something like that. Okay, that's the concept even in general relativity. So in general relativity, we call surface. What is surface? The surface is curve. So our 3D space and time, 4-dimensional space and time, 3-dimensional spatial and 1-dimensional time. It is woven together, like it is. So we live in the 4D space time, right? 4D space time, 3D space and 1D time. But bila ada curvature of space time because of some huge mass like black hole, like neutron star, so that space time curve into what? That is the thing that theoretical physics is thinking. Let's think like hyperspace, hypersurface, stuff like that. Okay. So tensor mathematics can handle this thing. This thing, it cannot be handled by vector already, kan? Macam mana dia nak handle vector? By handle R theta phi, which by itself is 3-dimensional space. Tapi tensor, we can handle this because it doesn't care about it's just the equation. It's just the rank of the tensor which can handle it. Okay. All right. So let's go back to tensor. Ni introduction why tensor is very important. So we talk about Einstein summation convention. Einstein summation convention. Okay, I just brief it. It is a lot. When we use tensor, it is a lot. Is a lot of thing, a lot of occasion when we use. I mean, it's all about using Einstein summation convention and the algebra of tensor. What is Einstein summation convention and inner product, outer product? What is it? What is it? Quotient law. Okay. Okay. Let's say A nu beta nu lambda. Okay. So let's say let's say mu is 1, 2, 3, or lambda is 1 and 2. So lambda mu. So how you want to expand this? What is what we call umbrella, or what we call umbrella, which is free indices. A dummy index. Dummy index. Very nice. Dummy index. Dummy index. So what is free index? So if you look at this, which one is dummy index, which one is free index? Mu? Yeah. Meaning that it is, the meaning of that is you can expand the mu, okay, by this 1 to 3. So this whole thing is talk about two cases. One is when lambda is 1, because lambda is free index. The other one is lambda is 2. So you can say this is, or this can be 1 b, okay, let's say we just expand first, okay, we expand this thing first. So this can be expanded by the free index first. So 1b lambda 1 plus 2b lambda 2, then 3b lambda 3. Okay. Can expand like that. Okay, so but we have lambda. For dummy index, we have 1, 2, 3. Now lambda we have 2. So that means this thing have two state or two conditions. One is when lambda is 1, the other one is lambda is 2. Okay, so it has two states. This can be A1 B1 1 plus A2 B1 2 plus A3 B3 1. Okay, and then the other one is A1 B1 2 plus A2 B2 B2 2. This is when lambda is 2. Lambda is 1. And the other one is 3 B3. That's how. Okay, got it? Easy kan? That is Einstein summation convention. Convention. Okay, now we look at the algebra. I mean, how we can manage the mathematics, the multiplication. We call multiplication is a inner product. We call it multiplication is like inner product. There are two kind of multiplication in multiplication tensor: inner product and outer product. What is inner product? Inner product is this, something like this. Okay, if you have mu, and then this nu, and then this is gamma lambda, and then nu. So the inner product is, this is inner product. Inner product is product between, okay, let's say for example we have this is what we call mixed tensor. Mixed tensor, one contra, and the other one is covariant. One contra, one covariant. This mixed tensor, one covariant. Rank 2 tensor. This is rank 2, and then multiply with another one. Let's say nu lambda gamma. So what happened? This is inner product. Multiply this kind of tensor, we call it inner product. Okay, they cancel, they contract. You can contract this one. So this one is what? Rank 3. This rank 2, rank 3, covariant tensor. So this is rank 2, and then this is rank 3. So all of them, if we multiply them together, it will be like 2 plus 3, like 5 rank tensor. But because of inner product, it contracts. It contracts by dummy index. dummy index contract it. So it contract by dummy index. Okay. So it become another tensor, only rank 3 tensor. Nampak? Got it? Faham? Okay. So kita inner product dia. So inner product. This is, maknanya kita inner product, maknanya kita this new lambda. And new kita boleh cancel, hilangkan dia. Cancel contract dia, panggil contract. Contract tu cancel. Kita boleh hilangkan dia. Jadi new, some other new tensor, tapi without the new. Kan sebelum ni we have like rank 2 tensor, ini rank 3 tensor, 2 plus 3 will be rank 5 tensor. Or if it is auto product, there's nothing can, if later we go to the auto product is nothing, there's nothing dummy index there. No dummy index. So ini dia ada dummy index, you see? Dia ada dummy index new. So dummy index we can contract. Faham? We can contract the dummy index. So contract dummy index, what left is mu, lambda and gamma. Mu, lambda and gamma. These 3. This is inner product. Outer product, let's say for example outer product. Mu and then outer product. We say, let's say B, some other thing lah. Dia tak boleh contract lambda, gamma for example. So dia akan jadi some other new new tensor, which is new mu sigma lambda gamma. So this is rank 5 tensor. This is rank 3 tensor. Okay, so dia inner product. Inner product there is always dummy index in there. Okay, so it cancel dummy index. What left is the index other than that dummy index, which is new mu lambda gamma. Now outer product, new mu with this. So they add together, everything add together, new mu gamma. So like rank 5 tensor, right? 2 ni rank 2, rank 2 ni rank 3, rank 3 contravariant, rank 2 mixed tensor, covariant, contravariant. Kita got outer product, we get new rank 1 1 contravariant and 4 covariant, rank 5 tensor. Okay, nampak? Very easy, kan? Very easy, just so for example, this one manifold, okay? I erase it. You can read a lot of article. What is manifolds? What is hyperspace? Hyperspace, very interesting. Kan? People, movie makers make a movie out of it. I first heard about hyperdrive when I watched Star Wars 1977. Hyperdrive. What is hyperdrive? It came from hyperspace drive, something like that. So, I mean, the notion of hyperspace, the things about hyperspace is already since general relativity, since Einstein general relativity, since 1920s, 1930s, since mathematics involved in higher dimensional space-time, math. Higher dimensional, not just space, higher dimensional space, math. It is in what we call differential geometry. Differential geometry. If you love math, you want to take some other courses math, want to be good at be theoretical physicists, differential geometry is a must course to take to study differential geometry. But differential geometry mostly it taught you in three-dimensional space. But if differential geometry to handle higher dimensional space, that differential geometry is using tensor, of course. Differential geometry. And other mathematics that is very good, that is deeper than this, is topology. They have topology, differential topology, a lot. Pure mathematician they learn this, but of course they don't care about physics. But we as a theoretical physicists, we learn this, and we also have to think about physics of it. Is physics make sense out of this, right? Okay. Okay, let's take another thing is okay. Another thing is let's go to the physics of it. The physics, how tensor is being used in physics, especially of course in general relativity. So in general relativity, I just give you a glimpse of general relativity. If you want to go, take the course. Okay? So maybe next semester I will teach next semester, because that course is what we call is elective course. So they can offer you all in every semester. Since I still here next semester, so I will teach. Anybody want to take that course? Welcome. Tapi itulah. But you have to have a math physics. This one. The other one is modern physics. But you take modern physics next semester, right? I'm going to ask program manager if you can go in. If some of you interested, I'm going to ask program manager whether you can go in my class. I think it's okay lah, because what important in that modern physics is the special relativity part. Even though sometimes people don't talk a lot in special relativity, I teach more detailed special relativity in my class. So it's okay. It's okay for you to join in. Okay, all right. Okay, in general relativity, yes, the best example of using tensor application of tensor is in the field of general relativity. So general relativity is we talk about space and time, and how this space and time interact with the physical thing, with the physical, like the mass, the energy, how energy affect space and time. Right? I mean, it is Einstein, when Einstein derived this equation, this famous equation, very long. It tells this is the curvature of space and time. This the shape of space and time, and it is got affected by this energy momentum tensor. They call energy momentum tensor. This is space-time curvature. They call Einstein curvature. Einstein space-time curvature, and this is energy momentum tensor. So the Einstein space-time curvature is got affected by the energy momentum tensor. What is energy momentum tensor? Is nothing but energy, which is mass. Mass is energy density, whatever constitute the physical thing that is the essence of matter. That is energy momentum tensor. So the mass, the energy density, the energy affect the space-time. I mean, when a black hole is something so massive. So you warp the space-time curvature. So the space-time, the warping of the space-time curvature, what we feel physically we feel as gravity. So gravity, we feel gravity because of of bumi kita, our earth, the mass of our earth, the mass GSIM of our earth warp the surrounding space-time, warping the surrounding space-time. So the surrounding space-time of our planet Earth kendur, distort, and we feel gravity. So gravity is defined as the warping of space-time. So kalau Newton, gravity is this. Gravity is force between two particles, two mass lah. Mass M1, M, big M dengan small m. So M1, M2 lah. M1, M2. So this is G M1, M2 over R squared. This is a Newton definition of gravity. Okay? G M1, M2 R squared. Newton, I think you know already. This one. So gravity as Newton perceive is a force. Okay? As Newton perceive. But Einstein perceive, it's not to say Newton gravity is wrong. It's okay. It's workable. We use a lot in our classical mechanics, right? But it's not something yang fundamental. The fundamental thing is the space-time curvature. The space-time curvature is mass. The curve the space-time. Mass. Okay, if space-time, if there is no mass, space-time is, we call it flat space-time. Flat space-time. Nothing there. And then we put some mass. We put a mass here. And the space-time start to warp. And the warping of space-time is the feeling of, is how we feel as gravity, how we perceive as gravity. Actually, if we put a Newtonian limits equation, this equation, gigantic equation of Einstein field equation, this thing what they call Einstein field equation. This K ni kappa ni is 8 pi G over C4. Today siapa yang attend my general relativity class, I'm deriving this thing, how people get this thing. Okay, but this equation, kalau we put Newtonian limit maknanya limit dia, kita we don't put gravity mass terlalu besar, mass about mass of Earth, mass about anything mass. This equation can come back, can be derived back to this equation. Maknanya general relativity equation, this K T nu mu is one whole general case. The special case is F G M1 M2 R squared. Special case je. Special case when bumi tak, gravity is not that strong. If gravity is strong, this equation cannot be done. We cannot use equation. Even the what you call the space probe that is now orbiting the sun, very close to the sun. You know, Parker space probe. You know, pernah dengar Parker space probe? Parker space probe, you have to search Parker space probe launched by NASA in 2018 to study the close study of sun. You boleh touching the sun, dekat, betul dekat. Tapi dia punya orbital dia ikut Mercury. Ni planet Mercury. You tarik dah Mercury. And dia sekali dia tak dia punya orbital mechanic dia tak boleh guna Newton lagi. Dia kena guna Einstein orbital mechanic, relativistic orbital mechanic. Just like planet Mercury. Planet Mercury because very close to sun, so the warping of space-time kat sun tu lagi kuat daripada bumi. Kuat daripada just simple body. So So the gravity wear or the warping of space-time is severe. Not that severe as black hole, but severe enough. So equation like what you call classical mechanics equation like classical classical orbital mechanics doesn't work. They have to use relativistic orbital mechanics. Kalau classical orbital mechanics kalau dia kata sun, Mercury planet, just dia punya orbital macam ni. Dia bertukar arah. Dia not stable. Kalau just classical mechanics, it just ellipse just like that. That's it. Every time just like this. Tapi Mercury dia always berubah. The space time, the orbital mechanics of probe, the Parker probe also berubah just like Mercury planets. In fact, they use a slingshot of Mercury planet to speed up, to accelerate. It can go the final velocity dia the sun is 700,000 kilometer per hour. That's the fastest man-made. I mean, not because man-made propulsion, but because of gravity slingshot. So fastest man-made ever object have gone through is Parker probe. That is around 700,000 kilometers an hour. Okay, go back to this. But a lot of things to tell, but the mathematics is this. Okay, a lot of things to story about to tell you about GR. Very exciting course, exciting subject in physics. It is in fact, general relativity is pillars of physics. The two pillars of physics is quantum mechanics and general relativity. That what makes up the modern physics at this moment. But the quantum mechanics make up the standard model. General relativity make up all the astrophysics stuff, higher dimensional stuff. All astrophysics, cosmology is based on GR. But those two cannot be combined. But there is a region where those two combine, which is what is inside the black hole, at the singularity. That is where quantum mechanics and general relativity merge to. But up till now, we cannot combine. We cannot do the correct. We cannot make up the theory that combine those things. Of course, we have a theory. There's a big theory. There's two big theory: contending theory, string theory based, and the other loop quantum gravity based. And there are so many other theories. But it is remain as a subject of theoretical physics. Subject of theoretical physics. Okay. Banyak cerita ni. Nanti tak sempat nak ajar. Okay. Alright. Okay, this is flat space-time. So flat space-time, we imagine, okay, metric. You know metrics? Metric is the metric. The usual metric, is this one, the arc length. This is metric. They call it metric. This is 3D matrix, three-dimensional metric. Three-dimensional matrix. So in general relativity, we symbolize this thing as d sigma instead of ds, d sigma square. Meaning spatial metric. And for flat space-time, we have this matrix, space-time metric. This one is called spatial metric. Is just like the x, dy, and dz. This is 3D lah, 3D. This is a between point. ds is a length between point. Is a length between point. Or d sigma. D sigma is between space spatial. This one d sigma, dx square, dy square, dz square is length between points. But in general relativity, between point, this one we call between, not just between point. If this one is between point A, between point B, that, but between this space and time, this is space and time A, is space and time B. The difference between, we call ds matrix, is different between space, we call different between points. But difference between space and time, we call it different between what? Space and time. Space and time, different between space and time. Event. Difference between event. Because event is about where you want to have your things, and when, and where and when. That's event. So today, the event today is now you are here. So you go back to some Pusanika is another event. Kan? That's between space and time. Because event. So ds here is difference between event. Different between event. Okay? Now you imagine, Now you imagine. You imagine a light inside my palm, inside my hand, a light, a source of light, and you is inside it, and then you open up. The source of light expand, right? Expand spherically, evenly spherically. The source of light expand at the speed of light. So, for example, here, that's how we define space and time. Okay, the source of light, and then it expands. It expands up to spherically when I open the thing. Ini by time. Expands spherically. So the radius of expansion keep increasing, which is this is what we call the radius. So the radius is what? So if you its radius is d is x square plus y square plus z square. Okay. So this is point A, and then you imagine after some time it goes to point B. This time x y z time time 1 time 2 x y z x y 1 z x y 2 x y z 2. I mean two different space and time, two different event. So this is ds. So if we look at this, the space and time, it combine. Okay, so r is how fast is r berkembang? The light travel at light speed c over some time. C time t dapat r tu. Nampak? C time t is r. C time t is r. So this is r is c time t. The light speed time cahaya. Time of the curve. So dia berkembang spherically. So kita boleh kata r square is equal to by by theorem Pythagoras, radius perkembangan radius of the sphere is r squared, or we can say c squared t squared is x squared plus y squared plus z squared. Okay, so okay, the CT squared, this is representing space. So CT is d sigma squared, which is dx squared plus dy squared plus dz squared. D squared, d sigma squared, dx squared, dy squared, dz squared. So, so kita boleh kata c squared minus d sigma squared is equal to 0. This is d sigma squared, d sigma squared. So c squared minus d sigma squared is 0. This menggambarkan photon ataupun cahaya itu berkembang spherically. Ct squared tu radius of the cahaya tu pergi, jarak cahaya tu pergi, and then minus dia punya space yang dia travel already. Okay. Dia macam ni lah, dia mula x, y squared ni dia menunjukkan the whole thing, but ini some portion of it, derivative of it. Okay. Dia tak perlu go to derivative of it. Dia macam ni lah, macam kita ambil derivative of it to explain space kan. Kalau you all ingat, the first day I taught you about this thing is position vector dot product with another position vector, kita dapat this one, right? Okay. So far okay? Okay.
How do you get R equals to CT?
This one, R is equal to CT.
Yes.
Okay, when the light come up, okay, the light goes spherically, light travel at c. So after y, after time t, so what is the radius? The light c times t. That's it. Very easy. Okay, that's how. So with this so this is, but there is more general case. C t squared minus d sigma squared is dipanggil ds squared. We call it ds squared. This is space-time metric. Okay. So let me go for the example. But you don't really need to fathom the physical meaning behind it first, because you have to think a lot. But I just want to show the mathematics of it. The mathematics. So we have ct squared minus d sigma squared is 0. C squared d squared minus d sigma squared is 0. But in more general case, generally we can say c t squared is c dt squared is c squared dt squared. Sorry. So dt squared, c squared dt squared. C squared dt squared, this is what you asked just now. C squared dt squared, right? Yes, plus c squared dt squared. This c squared is c squared d squared x is c squared dt squared. Now you got the difference. Okay. So c squared dt squared, more general, c squared dt squared, d sigma squared is ds squared. So this ds squared is c squared dt squared minus d sigma squared. So c squared dt squared in Cartesian coordinate, this one is we call dx squared dy squared plus dz squared. And in the spherical coordinate, usually in general relativity we use spherical coordinate, represent, and then we represent in tensor form. And this is d r squared d theta squared plus r squared sine squared d phi squared. Okay. This is ds. And this is what? This is the space, we call it in general relativity space-time metric. Space-time metric. See? So this is the spatial part, the spatial part, and this is the time part. It's spatial space-time metric for a flat space-time. For a flat space-time. Nampak? You all? Okay? Apa you, ini I just bagi the physics ni. Tapi but at this moment you don't need to know further the physics of it lah. Kan? You look at the mathematics. So see? Okay? So this is a flat space-time. What other space-time ni, kata space-time yang ada curve disebabkan oleh mass. So I give you another matrix. Ini matrix yang tak ada, ni flat space-time ni, this one matrix dia for flat space-time yang tak ada mass. There's no mass, nothing that can walk this space-time. This flat space-time. And this is the matrix for flat space-time. Okay, now we look at the matrix that is boleh padam ni this one? Okay. This is how we define space at the moment, tapi never mind. Okay. Yes. That is for example, the first person who proposed the space-time, so Einstein come up with this equation after very long. If you go to general relativity class, you know, after very long he derived this one. But nobody solved this equation until what the first mathematical physicist who solved this equation is Schwarzschild. Have you ever heard Schwarzschild? Benar kan? Schwarzschild. Best Schwarzschild. Yeah, Schwarzschild radius is black hole. Come up with matrix that tell how space-time curve because of mass. Okay, so space-time Schwarzschild talks about, and this space-time, warping space-time of this Schwarzschild matrix ni, dia boleh guna, can be used for black holes, not just for any. It's very generalized space-time matrix. So this M. So Schwarzschild came up with the law of derivation. I think whoever been to my general class, the time you have seen me derive the Schwarzschild matrix. So ds squared is see, kalau space-time matrix over there, flat space-time, very easy. So this is Schwarzschild. This is what we call the 2gm over r6 over 6 squared is the Schwarzschild radius. You pernah dengar Schwarzschild radius? Kan, Schwarzschild radius. Dalam black hole, whatever, anything, not just black hole, everything was Schwarzschild radius. Never mind, that's okay. This is the physics of it. You don't need to know the reality, but I just want to do the all kind of space-time metric. This is another space-time metric with mass. With mass, you walk the space-time. So the matrix, you know, the flat space-time very easy. I think it's similar to theorem Pythagoras. Right? This one is they got mass here. Right? If there is no mass. Okay, you put a zero here, you come back to that flat space-time. Nampak? If katalah mass is zero, so this zero, so goes back to same thing, flat space-time. Bila ada mass, you walk the space-time surrounding. So the what you call space-time, space-time metric tells how the shape of the space and time. Okay? So another example of a space-time metric is wormhole. This is my field. Although I got general relativity, master in general relativity. So wormhole, study wormhole. Wormhole is a very theoretical subject lah. It's purely theoretical. Space-time metric dia macam dia ada passageway. You go here, you come out the other side of the or somewhere space. There's wormhole. Have you ever heard about wormhole? I think a lot in science fiction, a lot. Kan? Stargate and all the stuff. Kan? So this is wormhole. What is space-time of wormhole? More complete, is E to C. Is what you call, you know, but I just give you is a redshift function. They call redshift function, and then the shape function of wormhole. You don't need to. I mean, you just look at the math. So there is function B is a function of R, and then divide by R. This function is called shape function, and this is R squared, the same thing. So this is a wormhole space-time metric. So let's see how we can generalize this thing. So we can use tensor mathematics to generalize this equation. How? To generalize. Okay. How we want to generalize this? We generalize. So see here the. Okay. Look at this space-time metric. So they have ds squared and dt squared, dt squared, and dr squared minus dr squared minus r. They have this that component. So that component is they have r, theta phi, theta and phi and time, right? Time and space. R, time, space r, theta and phi. So if yeah, okay. This one also. They have time. They have r, theta and phi, and they have something here. They have something here, and they have something in front. There's something in front, those dv. Okay. This one also, they have something in front, c squared. They have -1, they have negative r squared. They give r squared sign in front of those parameters, right? Parameters, differential parameters, dt, d theta, d phi. Okay. And wormhole also they have. These are the parameters, dt, the time and space, dr, d theta, d phi, and they have something in front, square, and there's no -1 will be r in front, and r squared, r squared. Okay, now kita boleh. So the parameters here is what? Is space and time, space and time, the space. R, theta, and phi. In tensor, we don't care about this. We symbolize differently. We symbolize it. Okay. So time space is space. So space is we start with R as 1. We symbolize it. We take it as 1. This take it as 2, take it as 3. Ataupun we call it x1, x2, x3, x1, x2, x3. x1 is r, x2 is theta, x3 is phi. This one time we always call x0. That is parameters, the parameters. Okay? These are all the parameters. So you will look at this parameters, dp, dr, etc. So for flat space time, we can say the so generally we can say ds squared is there's something here. Okay, tak apa, later I say. Let's say what it is. And then this is dt squared, dx0 squared, okay? And then plus something here, this x1 squared, plus something here, this x, and plus something else here, this dx3 squared. So this time this is dr squared, then dt squared, and this is dr squared, this is d theta squared, dv squared. Okay, nampak? Dr d squared here. And then what is this? This we define as what? This we define as metric tensor. This is tensor of it. Metric tensor. G mu kita kan, mu. So this is G00 we define. Sebab dia relate to time. So dx0 kita berkata dx0 multiply with dx0. And then this G11 dx1 multiply with dx1 plus G22 dx2 multiply with dx2 plus G33 dx3 multiply with dx3. Nampak? See? Nampak? This one, this. This G33. So, let's see the flat space time mudah. This is c squared. This is dt squared to dt minus dx dr. So dr minus r squared d theta okay, d theta squared tu d theta minus r squared sin theta d phi. Nampak? So we can say that G00 here is this one, and this is G11 here is this, and G22 here is r squared, G33 here is r squared sin theta. So we can say G00 is some books or some edition will say okay, x0 dia panggil time, but some books they some textbook in general relativity or in they kata x0 ni not just not just t tapi ct sebab dia nak sama. This is jarak kan, this length r theta and phi, dimensional here is space. So dimensional for space here is ct. So x0 is ct. So x0 is ct. Ct is x0, not just t. Light speed time t jadi jarak. So kalau itu maknanya dia tak ada lah. Sebab dia ada dct multiply with dct. Dct multiply with. So x0 here is ct multiple this G. So G0 here is 1, G00, G11 here is negative 1, G22 here is negative R squared, G33 here is negative R squared sine reduce theta. Begitu juga dengan wormhole, apa ni, kita ambil this one. So what is G00 here? Kita ambil cuaca wormhole, okay. Wormhole sama same thing, kita teruskan. So what is G00 here? What is G0 here? So kita boleh tulis, okay, tulis dulu. This is equal to G00 dx0 dx0 plus, ini plus G11 dx1 dx1 plus G22 dx2 dx2 plus G33 dx3 dx3. Okay, G0 here is what? System. So G00 is 1 minus 2gm over RC squared. Okay, so G11 here is negative 1 over 1 minus 2gm over RC squared. The X0 ni sudah masuk, dia absorpsi dalam tu. C squared masuk dalam dt squared. Jadi D C squared dt squared. Jadi kalau kita masuk sini, that's why D C squared dt squared ni sudah masuk jadi D C T squared. This one is X0. That's why G0 dia tak ada C squared. That's why C dia absorb inside here. So 1 minus 2gm over RC squared and G1. So this one is negative G22 is negative 1 R ganda 2 R squared. G33 is negative R squared sine squared theta. Okay? Okay, pada tu boleh.
Dah ambil dah? Apa? Gambar? Ambil gambar yang bawah.
So, the space-time matrix can now be rewritten as this. ds squared is G00 dx0 dx0 plus G11 dx1 dx1 plus G22 dx2 dx2 plus G33 dx3 dx4. So how we can okay. So this is, kalau you look at this, dia macam diagonal of this 0, 1, 1, 2, 2, 3, 3. Kan? Dia boleh jadi more overall generalization. Tapi dalam physics, there's only diagonal. Tapi kalau ada rotation, dv dt, dia ada dv multiply dv, dia ada rotation. But if there's no rotation, only dv squared, purely diagonal. Generally, okay, general diagonal is like this. So we can write this thing, we can, in more general form, we can write this as G00 dx0 dx0 and then plus G11 dx1 dx1 plus G22 dx2 dx2 plus G33 dx3 dx3. Okay, and then it's going to be plus G01 dx0 dx1 plus G02 dx0 dx2 plus G03 dx0 dx3 plus G10 dx1 dx0 plus G11 is plus G12 dx1 dx2 plus G13 dx1 dx3 plus G20 dx0 dx2 0 plus G21 dx2 dx1 plus G22 dx plus G23 dx2 dx3 and the last sentence plus G30 dx3 dx0 plus G31 dx3 dx1 plus G32 dx3 dx2 and then G33. This is overall space-time metric. Okay? Tapi yang ada dalam fizik, what is inside fizik is this only. Others G01, G02, G03 nothing, tak ada, zero. Yang wujud dalam space-time matrix only, this is time, is space. Diagonally. Tapi dia add all overall. If we want to generalize this, we can generalize it this way. Tapi what this portion of it is just diagonal part. So this whole thing we can rewrite in Einstein summation convention as what? So kalau kita tengok, if you look at this one is 0, 0, 0, 0, 0, 1, 0, 1, 0, 2, 0, 2, all are dummy index. So if we add up together, so we can write this whole thing we can write as ds square is G nu mu dx nu dx mu. So this is the general equation of metric. The equation of metric. General equation of metric, space-time metric, partial metric, whatever, is general equation. Then we write in tensorial form. See, mu is di kontra, di echo, di kontra, dia upper index, lower index, upper index is dummy index, both of them. Mu dummy index. So we can expand. So this is the general equation of metric. So metric times metric, space-time metric is that one. So G00 tadi, okay? Just a simple flat space-time, very simple. Wormhole, black hole, Schwarzschild metric is this one. Schwarzschild metric. Schwarzschild metric. Space-time metric. Okay? Okay, everybody? Okay, boleh? Tak faham, come to my office anytime. No. So this one is how you use tensor mathematics to calculate things in general relativity lah. Okay, so we know this is what we call this metric. the equation of metric. This is metric tensor. Tensor. So, so what is this metric tensor? What is this metric tensor in metric tensor in the partial differential? What is this metric tensor in partial differential form? Partial derivative form. Okay, actually metric tensor is present. So there is a space. So this is a position vector. Could be this position vector. These two position vector try to explain what is this surface about, the characteristic of this surface. So there's maybe there is position vector of this direction and another position vector of this direction. Direction it become so yes. If there is two vector, it can define the surface. Two vector can define the surface. Okay, two vector is so these two vector, two position vector can define a surface of now is a four-dimensional space, time and space, time and space, so space time space, hypersurface, hypersurface tadi. Maknanya dia not just space. This is two-dimensional. I mean, four-dimensional, 4D space-time hyperspace. Maknanya each point of this dia ada time, dia ada R, dia ada theta and P. Dia ada time, ada R, theta. Each of this, each point of this. So dia tensor dia handle four-dimensional space. So this R. So if even dalam in our the first day I talk about the metric and position vector ni position vector. Okay. Ini just refresh your position vector stuff. You can say this is dxi position vector, yj, dzk, dot product ni. Dot product dxi, dyj, dzk. Ini dot product. You dapat ni boleh kan? Right? So this is position vector. dr dot product is dr and dapat dari s square. Ini generally and it applies also in space and time. This is space. This is space only. And I taught you in the first day, first two lectures. I taught this one here. dr dot product dr. You go play this one. And this is, can you apply this in tensor also? Even in high dimensional space, not just 3D. This 3D. So we can say ds square is dr dot product is dr. Okay, ds square is dot product. Okay. Okay, I erase this one. I erase this one. Okay. So that one. So kita boleh kata ds square is dr dot product dr. In tensorial form, kalau a dot product is b in tensorial form, kita boleh tunjuk a inner product is b whatever lah, mu, ini product is apa? Lambda or whatever simbol ada guna lambda simbol. Lambda, so lambda is 1, 2, 3. Ni for vectors. Okay. So kan daripada sini I tunjuk tadi the first I show you the first lecture tadi, the first hour of lecture, lambda dengan b lambda, the contract is meaning the contraction of contravariant dengan covariant of a tensor, rank 1 tensor is equal to macam dot product between those vectors, kan? Alright? So kita boleh kata dr lambda no more dot product, okay? Sebab ini in tensorial form. So ds squared is dr lambda and r lambda or r lambda is a function of x mu. R lambda is a function of R lambda is what is function x mu. So kita ambil this R lambda, R lambda, lambda kat sini is a function of x mu. Lambda kat sini kita nak beza ke, just put a little difference, x mu. Actually mu and mu is same thing. Mu is 0, 1, 2, 3. Mu is 0, 1, 2, 3. Right. So just symbolize to make it generalize. So we symbolize can be one with multiply, can be an array of matrix written. So okay, right. Okay, now kita ambil this one. ds squared is okay. Oh, sorry. It's not sorry. It's R lambda. R lambda is function of mu. R lambda is function of R covariant. R is function of. So covariant then R ni R lambda is a function of x mu. Then covariant pula is R lambda is function of the beza sikit mu. But the thing is the same actually. Mu and mu is the same thing. Okay. So just beza contravariant, covariant. And this now the dot product. This is the vector. This is the tensor. Okay. And then by Chayes rule, which is very important, dr lambda, you can say dr lambda is dr lambda partial. But jadi banyak 0, 1, 0, 2, 0, 3, 0, x0, x1, x2, x3. Jadi dia banyak derivative. So x mu dx mu, and then the r lambda covariant is dr lambda dx mu. Now kita masukkan balik dalam sini. So ds square is equal to dr lambda dx mu multiply with dr lambda dx mu. So we have dr lambda dx mu, dr lambda dx mu, and then dx mu. So this is what equal to g mu dx mu dx. So what is this? So g mu is it? dr lambda dx. New dr lambda dx. So this is the partial derivative representation of the space-time matrix tensor. Faham? Okay? Faham? Ini kalau dia punya partial differential dia. Kalau you tengok sini, dia punya apa? Dia punya dummy index dekat atas dia. Bawah ni both is a free index. Okay? So ini satu. Tunggu lah. Betul. Okay. Okay. Now, now you go to this one. This is another the first object tensor, object. Maknanya bahan tensor yang pertama dalam dalam general relativity. Banyak digunakan lah. The metric tensor. Dia represent pada tadi lah, 1 to GM, G00, X1. So kalau dalam flat space time, so ds square, more general case kita start di new function of r, symmetric dia, jadi c square d square. Sebut kalau kita tak nak guna c square pun, sometimes c square ni dia anggapkan sebagai satu. Dia buat benda tu kalau dalam calculation later after the final ke baru kita pasuk plug in the c square. Tapi dalam calculation kita tak nak gabung, the c square is just a constant. We take it as 1. So untuk memudahkan, jadi tapi kalau kita masuk pun okey. It's okay. What this one is dct square, dxo. Okay, satu lagi e lambda is function r, ni more general matrix is dr square minus r square d theta square minus r square sin theta d phi square. Mana this is general matrix. General matrix kita define flat kalau e vr is to 1, e lambda r is to 1, yang lain sama same. Kalau macam matrix what they call itu structure matrix, e vr is equal to c squared 1 minus 2gm over r c squared, and then e lambda r is 1 minus 2gm c squared r, and then yang lain tu same thing. That is if in more general case dia tulis itu. So dia ada function, exponential function, maknanya exponential function of this is matrix. This one is matrix G00, this matrix D11 is negative E lambda R, matrix G tensor matrix tensor G22 is negative R squared, matrix tensor G33 is R squared sin inverse theta. Okay, so this is more general. Maknanya benda ni kita tak tahu apa, tapi it doesn't matter. If just take it like this, in terms of mathematics, mana kita boleh manipulate dia, how kita nak manipulate to calculate something else. Okay. Then another what we call kalau if this is space-time matrix, kalau you all belajar dulu or darjah dulu is curvature. Kan? The first day is a curvature. Curvature is 1 over rho ataupun 1 over r. R of this is curvature. Okay. Kalau dalam general relativity, curvature dia not just 1 over r, not just one dimensional space. Jarak satu jarak ni one dimensional saja kan. R ni one dimensional. Tapi kalau dalam in general relativity, dia four dimensional curvature space. Not just one dimensional. Ni line curvature. One line curvature only dia punya 1 over r ataupun 1 over ni radius curvature radius. 1 over r. 1 over. Tapi kalau general relativity, space time curvature is dipanggil Christopher symbol. Mu lambda gamma whatever lah. Tapi dia adalah rank 3 object. Dia orang tak panggil dia tensor, tapi dia is the rank 3 object which is can be manipulated with tensor. Daripada Christopher symbol ataupun connection ataupun connection, fine connection, macam-macam orang panggil dia fine connection. Tapi dia menerangkan space time yang curve. Dia menerangkan curvature of the space time. Jadi tadi saya tunjuk kita buat calculation by using tensor calculator, kita boleh buat calculation. Tapi dulu buat tadi lah. Ini okey okey. Ini sini tuan. Okey, kalau nak dalam dah. Ini ke ini? Ini This is what we call the curvature. Kalau dalam space time curvature macam ni kan. Space time curvature kata dia curve disebabkan oleh something lah, boleh some mass ada kasi dia curve. What is the curvature of here? Curvature of here is curvature yang represent by line, space time line. Space time line dia. This is x mu. Maknanya that point ni adalah x mu. X jadi x0, x1, x2, x3. Maknanya di ct r di theta di phi. Dia tak satu point, each point of this. And dia based on line. Tapi dia ada satu lagi objek yang based on surface. Space-time surface. Based on space-time surface. Ini curvature juga, tapi based on space-time surface. Macam ni, this one is space-time surface, hypersurface lah. Hyperspace. Dia kata hyperline. Not just one dimensional line, hyperline, hyperspace. Curvature juga. This one is curvature, this is curvature, this is also curvature. This is more generalized curvature. Even Einstein tensor also curvature. Tapi Einstein dia more, actually Einstein is about this. This is before Einstein tensor ada kita tahu which is that Christopher symbol. Is also curvature. Mu lambda gamma. They represent curvature. Actually, they represent this curvature is not. This is second kind. Very first kind. Yang to represent it is the first kind. lambda whatever mu gamma. Maknanya dia one contravariant, two covariant. This is representing the curvature. Tapi I tak perlu you tahu the physics of it kan, the mathematics of it. I nanti. Okay. Pada mana? This one? This one ke this one? Dulu penting. Okay, this one is Riemann tensor. Right here, Riemann means lambda, beta. This is Riemann tensor, which is also a space-time hyperspace curvature. Curvature of space-time hyperspace. Ni curvature. Correction is curvature of space-time hyperline. Kalau you belajar yang first day tu is kappa saja. First day you belajar kappa. This one is kalau space-time hyperline is Christopher symbol. This one Christopher symbol. This one is Riemann tensor. This one is a tensor. Riemann is mathematician. Riemann tensor. Dia lagi detail. Okay, now kita try buat some calculation. Pada this one, okay. Pada atas. Boleh ya? Lupa bawa chalk. Okay. Now, Christopher symbol. What is Christopher symbol? Actually, Christopher symbol mu lambda gamma boleh ditulis sebagai half kaitan dia dengan matrix tensor. How does it relate with how Christopher symbol relate to matrix tensor? Is dx gamma g mu lambda plus dg mu gamma dx lambda minus dg lambda gamma lambda dx. So g gamma lambda g mu is equal to g mu. Same thing. Dia boleh tukar. Boleh same thing. So this one is dr lambda dx lambda dx mu dx mu is equal to dr. Jadi lambda di bawah ke atas pun tak apa, di atas dia tak penting, not just to contract with it, doesn't care. That's why kita boleh tulis dia adalah symmetric. So this is the equation. So this one g mu this one is all this about yang tadi. Okay, now let's say for example we have this matrix. So this is matrix. This is G 0 0, G 1 1, G 2 2, G 3 3. So this is the matrix we have. Okay, for example, we want to find, okay, generalized equation for this. How we want to find, for example, we want to find this one. We want to find the first, this is Christopher symbol first kind.
Daripada doktor. Cuba cek.
First kind. So Christopher symbol second kind is okay. How we want to say is lambda mu is sigma mu sigma sigma lambda gamma. How does it relate to this? How does this relate to this? By contraction. G alpha mu net mu lambda gamma. Okay? Gamma lambda gamma ini sigma lambda gamma. This was sigma mu lambda gamma. Mu dengan mu contract. Mu dengan mu contract. Mu dengan mu contract. Okay, nampak? You nampak? So this how the first kind, the second kind, Christopher symbol. This is first kind Christopher symbol. First kind Christopher symbol. Okay. Nampak? You okay? So okay? Alright. So kita ambil contoh calculation. I naik atas okay.
Gambar, gambar.
Okay. Okay. Wait. Okay, everybody.
One shot.
Okay. So, kita boleh tengok sini. Sigma lambda is equal to G sigma mu sigma lambda. So kita boleh expand dia. Kita boleh expand semua. Kita tahu every benda ni all semua dia adalah space time. Sigma, lambda, gamma, mu, whatever semua ni dia adalah 0, 1, 2, 3. Right? So sigma pun 0, 1, 2, 3. Lambda pun 0, 1, 2, 3. Gamma pun 0, 1, 2, 3. Mu pun 0, 1, 2, 3. Space and time. Time and space. Okay? Maknanya all ni, tapi kalau kita tengok equation ni kita boleh expand kat mana? Mana dummy index dia? Tak tahu. Which one dummy index? Gamma mu lambda. Mu ni, right? Betul, mu. Mu is the dummy index. The mu is the dummy index. Which we can expand. Maknanya kita boleh pilih this one. G sigma 0 lambda sigma plus G sigma 1 lambda sigma plus G sigma 2 lambda lambda gamma plus another one is G sigma 3 is 3 lambda gamma. Betul tak? Everybody? Faham tuan? Okay. Okay? So, kita boleh derive, kita boleh tunjuk equation. So, katalah kita nak katalah kita nak cari, so this is the general equation dia. Okay. So kita nak cari, katalah kita nak cari 1, 1, 1. Sigma is 1, lambda is 1, gamma is 1. 1, 1, 1. 1 ni juga ada simbol pada R. R. The same thing kalau kita 1, 1, 1 maknanya dia beza dengan this one is radius. 1, 1, 3 kita kata. 1, 2, 3 maknanya this one is radius, theta and phi. Jadi kita boleh tulis. So sometimes we simulate R, theta, phi. Okay. 1, 2, 3. 1, 1, 1. So now contoh yang kita ambil, what is 1, 1, 1? Base metrik dia atas yang tadi, this one. Which is G00, this one, VR, G11. Okay. So maknanya lambda dengan gamma is 1. Sigma also 1. Ini all kita letak sini. Jadi kita letak sini. Sigma, ini 1, 1, 1. 1, 1, 1. G, sigma kita letak 1 lah, 1, 0. And then sigma 0. 0, sigma is sigma is 0. This one 1, 1. Okay. This lambda gamma, this one is sigma is 1, lambda is 1, gamma is 1. So kita nak kira this one. Plus G 1, 1, 1, 1, 1, 1 plus G 1, 1, 1, 2, 2, 1, 1 plus G 1, 3, 3, 1, 1. Nampak? Apa ini? Soal. Apa ini tuan? Everybody nampak? So, okay, this one asal dia express ni. So kita ambil sigma is 1, lambda is 1, gamma is 1. So you just plug in lah, 1 for 1. Kita dapat ni, one. Now kita nak buat calculation. Kalau kita tengok sini, kita boleh cancel out main thing. Apa yang kita boleh cancel out? Dia 0, mana dia 0. Kalau you tengok sini, kita ada G0, G11, G22, G23, okay. Ini contravariant matrix cancel. That one is covariant matrix cancel. So relationship dia very easy. Kalau di diagonal matrix, this one is diagonal dia operate diagonal dia very simple. G new mu contravariant is equal to terbalikkan ni yang G new mu. Okay. In the first place, G10 ni, G10 apa? Tak ada. Nanti. So, maknanya kita tak perlu ada sini. This one tak perlu ada. G12 pun tak perlu ada. G13 pun tak perlu ada. So, ini saja. Nampak? Everybody? Semua boleh. Dia diagonal matrix. Only diagonal matrix. Only diagonal. Okay? So, ada G10, G12, G13 kosong. So, only G11. So, now, do the question. Tapi sini lah, pada sini. Okay. Sudah kita biar. Kita beri contoh calculation. Approach this one. Okay. 1, 1, 1. What length is this? 1, 1, 1 is G11 multiply with 1, 1, 1. Okay, G11 is what? G11 is this one. Okay, negative 1 over E lambda R. But G11 is yang ni. So kalau G11 contravariant is baliklah 1 over E. Multiply with 1, 1 this one. Macam mana nak calculate this one? Kita boleh tengok calculate this one macam mana tahu. Kita guna formula ni. This formula is half G X lambda G mu lambda gamma plus G X gamma G mu lambda minus G mu G lambda gamma. This formula dia. Tapi very easy to remember. So with mu, tengok mu dekat bawah tadi mesti minus. So what left is lambda dengan gamma. The first could be anything. Lambda ke gamma, kalau kita ambil gamma, gamma what left is mu lambda. Mu lambda, mu gamma. Gamma mu lambda. So now how we want to, this is the equation, the formula. Kita go to formula for 1, 1, 1. 1, 1, 1. 1, 1, 1. 1, 1. So this is 1 half. Macam mana dapat formula ni? Itu you kena belajar general relativity lah. I will show you general relativity. So this dx1 g11 plus, so for this is mu, this is lambda, this is gamma. 1 will be x, 2 d1, x1 juga. 1 tak ada. 1 minus dg11 dx1. Very easy. So ini kita cancel out. Tolak. Tinggal ini saja. 1 over 2 dg11 dx1. 1. So macam mana kita make calculate ni? What time? Oh, very fast. Okay. Okay, every contoh satu contoh. So, 1 is 1 over 2 G11 dx11. So 1 over 2 is what? 1 over 2 is G11 is what? G11 is D negative D lambda R respect to 1 R. So G11 I mean this is what? This is 111, right? This is 111 111. So G11 is G11 11 1 is equal to G11 is 1 over E lambda R. Lambda R negative multiply with negative E lambda R. Okay. Divide R and then multiply with E negative lambda R solve this.
Yang ingat nak tengok.
Dapat.
Yes, kan?
Okay. Okay, dekat dia tu je. Ada depan dia ada kelas? Ada kelas? Oh, okay. Oh, okay. Itu tempat nak mengajar anggapan Riman. Tapi tempat 70